Ladies and gentlemen, after looking at the different system technologies, now follows a lecture presented by Mr. Volker Lehmann on solvent cleaning processes for precision cleaning applications.
Thank you, Gaudens, and hello to everybody. So, what is the subject? Subject is nothing new, solvent cleaning, but in this case for precision applications. So the question is, are precision applications really a fit for a cleaning with solvent processes? So first, we want to introduce the common areas of applications for solvent cleaning systems in order to give you a background. What you see here is on the left side a picture of one of our systems. It's called the Ecoclean, which is one of our machines for the solvent cleaning machines program. And in the middle, you see the main components of this machine. So first, it's the working chamber, marked with 1. This is the place where the whole cleaning and drying process is done. And then second and third, the flat tank, the 2 flat tanks, and the corresponding pumps with marked with 7 and 8 to fill and empty the working chambers out of the flat tanks. Marked with 4 is the distillation unit, which is responsible for the vapor degreasing and the regeneration of the system. In addition, we see the marked with 10 and 9, the drying condenser and the corresponding vacuum pump, which is the responsible drying feature of the machine. And in addition, we show you with 11 the heat recovery system in order to make the machine more energy efficient. And also you see the water separator to take out the water, marked with 6. And optionally, we also show the continuous oil discharge unit, which can dispose the oil during the operation of the machine. All these systems typically work nowadays with hydrocarbons or with modified alcohols. So the process, in order to give you a better, even better impression of how such systems work, the whole process is done in the working chamber. So the working chamber is getting loaded with the baskets, which include the parts or carriers or fixtures or whatever. Then the door is getting closed and sealed, and the process starts. The first step is that we evacuate the working chamber through the vacuum pump. So in order to have a vacuum in the whole system, the whole process does work under vacuum. So the first process step is that we pump the fluid from the first flat tank into the working chamber, and then the mechanics can start. We can rotate or oscillate the parts, we can do an ultrasonic treatment, or we can do what we call an injection flat wash, which is pumping the fluid through the pump, through the filter, back into the system to create a high turbulence in the machine. After the process step is finished, we empty the working chamber over pump, filter, back into the flat tank. So every single step is filtered. The same thing can be done out of flat tank 2, which is marked with 3. And finally, the last cleaning process step is the degreasing done out of the distillation unit. There, the vapor is getting into the working chamber, and thus the final degreasing of the parts. After this process, we dry the parts through the drying condenser to get the vapor condensed and getting taken back into the system, and through the vacuum pump to dry the parts with the final drying pressure. After that, you vent the system, the working chamber, over air from the outside. You open the door and the parts come out clean and dry. So solvent machines are typically being used in mass production components fields, like turn parts, milling parts, grinding parts, but also stamping parts, pressed parts, deep drawn parts, bended parts. and also a group which is called the hardware or fasteners, like rivets, bolts, nuts, screws, nails, and also for fittings, couplings, small pipes, profiles, and so on. These are typical applications to clean these parts after machining with a solvent cleaning system. So in the middle, you see a picture that really demonstrates what a typical application for such a system is. So you see screw machine parts, press parts with a lot of oil and chips. And after the cleaning, the parts come out bright and shiny and free of chips. So by visual inspection, you consider these parts are perfect. So typical requirements to these machines are you need a high throughput in order to handle these lots of thousands of parts. You need to be able to handle a lot of contamination, like chips, particles, and oils. And the cleanliness levels that you need to meet are typically particle-wise bigger than 200 micron, and the surface tension in the range of 38 millinewton per meter. What does that mean in regards to the system? The system needs to be able to be fast. That means you need pumps with a high pump rate. You need a high energy of vapor in order to heat up the parts fast. And you need a high regeneration capacity to keep up with this high volume of contamination that you take in such machines. So, but lately, an increasing number of requests comes out of precision markets. Why is that? Filmic contaminations are getting more and more important to precision markets, and therefore, since solvents are typically perceived as good degreasers, it's obvious that customers think, well, it also should be a good solution then for my filmic contamination requirements. Especially these requirements come out of the high purity industry, which are high vacuum components built into wafer steppers, gas chromatographs, mass spectrometers, high power lasers, and so on. The method to measure the filmic contamination is RGA, residual gas analysis, which measures extremely low concentrations of hydrocarbons that are still on the parts. Another field is cleaning prior to PVD coating, which are typically automotive parts or tools. There, the measurement is typically done with microscopic measurement or with contact angle measurement. And finally, also medical applications are a concern. Medical instruments, medical implants are getting machined, and after the machining process, they need to get cleaned, and this can be done with a solvent process. The measurement there is by measuring the TOC value of the components on the parts. So in order to make it more transparent, we have prepared two examples for you. The first example comes out of the high vacuum technology. And we used a reference part, since there are so many different various components. A reference part has been designed to be able to get a good feeling if this is a right process, if it works or not. And this part has been machined with blind holes, threaded holes, through holes and bars and so on, in order to make it as complicated as the real parts. And the contamination was always the same. It's a little bit of processing oil and particles. The machine we used was a solvent machine working with modified alcohols, and the solvent was not fresh. We regenerated the the machine as good as possible. So we took the oil out through the continuous oil discharge unit, and we changed the filters in order to have a good as possible quality of the solvent in the machine. And after the tests, we measured the outgassing rate, which is the RGA measurement, at a pressure of 10 times minus 12 millibars, in order to see if we comply with the specifications. As you see on the right side at the bottom, this is a fairly good result, but it wasn't just good enough. Next example was cleaning of a automotive component, injection component, prior to PVD coating. So what we did is we tested the real component, which was also grounded and had holes, and the contamination was very little since the parts have been pre-cleaned and were fairly clean. Only particles, dust, and a little bit of grease out of the air had to be removed. Again, the trials have been done with a machine using modified alcohols. We did the same thing. We only regenerated the machine. We didn't use fresh solvent. The cleanliness requirements were the parts had to be free of oil, free of grease, and no particles bigger than 50 micron after cleaning and prior to coating. What was the result? Well, we were extremely concerned with the high requirements in terms of particle contamination. This wasn't actually the problem. The problem was that we found isolated small drops of oil that remained on the parts by a visual inspection under a microscope with 100 times resolution. So again, it was a very promising result, but not good enough to be able to coat the parts after these tests. So the summary is the results were not bad, but also it was not good enough. So are these systems now suitable or are they not? Luckily enough, neither our customers nor we were willing to give up. So we took the tests and we identified what are the issues. What were the issues? Why didn't we get the cleaning results we needed? So first, it's clear there must have been some oil left in the distillation, which we also could we could detect it. So what does that tell us? The continuous oil discharge unit is not able to take out 100% of the oil out of the system. But is this the only issue? No, definitely not, because the last cleaning process is done through the distillation unit with the vapor degreasing. So there must be the issue. There is still some oil left, we figured that out, and this oil must get on the parts. Either way, this must be the issue. So we identified all the parameters which concern the quality of the vapor, and these are the height of the distillation tank, the surface of the evaporation surface of the solvent, the pressure difference between the working chamber and the distillation, the heating power that we introduced to the distillation, and of course the flow of the vapor. And all these items we optimized by increasing the height of the distillation, by increasing the diameter, by reducing the pressure of the pressure difference of the working chamber and to the distillation, and by regulating the heating power. And finally, we also optimized the baffle plates in order to make sure that if oil is getting into the vapor, that we still are able to keep it back and not exiting the distillation. Another step we made is precision applications do not require only filmic restrictions, but also particle contamination. And so we also looked into this area. What can we do to improve the particle contamination level of such solvent systems? What did we do? First of all, we looked at the whole design of the construction of the machine and made sure that we avoid any kind of dirt formation in the system. Secondly, we electropolished the working chamber in order to avoid that there is any deposit on the working chamber wall that can cause recontamination. In addition, we selected the right filters that can be used, and we adapted the filter performance in order to not overflow the filter. And another step was we used suitable holders for the parts and did a redesign of the rotation frame in order to make it more accessible to the parts and create less particles. We also optimized the vacuum technology, and finally we eliminated all use of non-ferrous metals in the machine. What is the conclusion? Well, I wouldn't stand here and tell you, well, all this didn't work. Of course, obviously, we had a good result. And so the conclusion is, here you see a comment of one of our customers who actually use such a precision solvent cleaning machine from us, Ecoclean Core. And he cleans high vacuum components, and the result did exceed the expectations. He doesn't only reach grade 4, but grade 2 cleanliness requirements from ASML standards. And grade 2 are the most stringent filmic requirements actually out there in the high vacuum industry. The conclusion is, with a compatible intake of contamination, solvent machines can definitely be a solution to clean very high filmic particle requirements from the vacuum technology, thin film coating, and the medical components. Especially the lower investment costs and the lower running costs are a very appealing factor that makes the solvent cleaning systems definitely very attractive as an option or alternative to aqueous systems. Thank you, and looking forward to your questions.